What I would like to talk about here is about high performance accelerators with reduced energy consumption. See. Okay, so this is an outline. I will start with some thoughts on global warming and how the accelerator community can contribute to reduce carbon emissions and combat global warming. Energy efficient accelerator technologies and concept is one way we can contribute. I will then go to some examples. First, of course, close to my heart is RIC, the first collider that uses two superconducting accelerators and has reached record luminosity with advanced beam cooling techniques. Say a few words about ERLs, which is one of the prime concepts, accelerator concepts that reduces power consumption, but still has the potential to produce very high brightness electron beams, even though it would consume much less power. A few words about C beta, but I won't say too much about it because that was the topic of the colloquium last month. And then the rest of the talk will be on ERL, electron-positron collider concept. A few of us have developed this concept over the last couple of years, and it combines the advantages of a storage ring and linear colliders while greatly reducing power consumption. But first, as I mentioned, a few words on global warming, and this is very much a personal view. On a very global scale, and this is truly global, energy flow and entropy, in fact, are the key factors of life on Earth. Over the last 250 years, something very unprecedented happened, namely the availability of essentially unlimited amounts of fossil energy. And that has greatly distorted the way we use energy. All life on Earth uses energy in a way to sustain itself, but now we have energy, more energy than we need to sustain ourselves. And so that changed how we use it. And in fact, it led to what I would call a profound addiction to this unlimited energy supply. And it led to have very serious consequences. One of them is population explosion, but also a lot of wasteful energy use. So this led to actually to a threat of really catastrophic consequences from a possible runaway global warming. And that simply requires that we stop extracting fossil fuels as soon as possible. And the graph below is just one of the many graphs that are being published of the temperature anomaly in Earth. And we are now more than a degree Celsius above pre-industrial values. So what could we do? I want to start by saying that we owe a very big debt to the climate scientists of the world because they have established the existence of global warming and its connection to the use of fossil fuels. They established a scientific consensus of that, and they did it based on scientific methods and with a strict peer review. That was not very popular, but they stuck it out, followed science all the way, and were and still are attacked for their work. It seems to me now we have to find solutions, and that's really the job of a scientist or maybe more specifically physicists that now need to help develop global and scalable solutions. A very important aspect. It has to be scalable to the whole world. And again, that needs to be done based on scientific methods, fact-based, and with strict peer review. And that, of course, is happening. But again, some of that will not be popular. And we as a community, have to be prepared to be.
Like a parameterized sweep of, okay, this is around 3.
I think somebody needs to mute in the back.
Heat flow is. Yeah, we do that. Yeah.
Okay. So a very simple view is that human-caused CO2 emission is mainly a product of 3 factors: number of people, the energy consumption per person, and the CO2 emission per energy produced. They all contribute, and we can address all of them to reduce the CO2 emission. And there's a real urgency to do that. So, for example, actions that we should take immediately is reduce and reverse population growth. That's for the first factor. Second factor, reduce energy consumption per person by increasing energy efficiency for all activities. And in this case, I mean, also when we build new facilities as a community, we have to build them as energy efficient as we can. And then finally, in terms of energy sources, switch to carbon neutral energy sources on a large scale. And again, large scale is the key word here. So I already mentioned that we should apply maximum energy efficiency to new scientific facilities as well. Just a few words of atmospheric CO2. And I think if one wants to take a fact-based approach, which we have to, of course, we need a measure of how well things work. And atmospheric CO2 is, I believe, the best measure we have presently to test the carbon, to measure the carbon intensity of the energy use. So atmospheric CO2 is highly correlated with the use of fossil fuels, as well as increased global temperatures. And in this picture, you see that this increase here matches the increase in temperature, but also the increase in fossil fuel use by the industrial world. And now more and more across the whole world. You have to be aware that carbon is continuously exchanged between atmosphere, plants, soil, and oceans. However, the removal of carbon from that cycle is very slow. So that means that the annual CO2 growth in the atmosphere is a direct measure of the human-caused CO2 emission. And again, human-caused CO2 emission is simply the number of people times the energy consumption per person times the CO2 emission per energy produced. So what I did in this graph here is to show you in the red curve the annual CO2 growth in ppms and including a trend line, just a straight trend line, and compare it to the population, world population growth in billion. And you can see, as expected, CO2 growth is dominated by population growth. However, there is a slight difference in slope, as you can see. So in fact, the CO2 emission is growing faster than the population. So what could that be due to? I mean, increased energy use per person. This is more and more people are using more and more energy, as in developing countries, for example. And that may well be partially offset by improved energy efficiency in developed countries, probably primarily Europe, but also the US has improved their energy efficiency. Another explanation, and maybe it's the combination of these two, in this early area, there was a really substantial use of hydro and nuclear power, whereas those two energy sources have stagnated over the years, and the increase of coal is increasingly used as energy, and that could also explain the increased emission. But I note that in the later years here, there is no sign that the introduction of renewable energy sources, such as solar and wind, that introduction has reduced human-caused CO2 emission in these years, even though it's still a small part, but it's starting to be a substantial part of the energy production actually comes from these sources. No effect on CO2. That's something to keep in mind. And so let me now go to what we as and the accelerator community could do. For population growth, very little directly. It has been shown very successfully that supporting women's rights and education worldwide is the best way to address population growth. For energy efficiency, there we have clear opportunities. So we can focus on the development of energy efficient accelerator technology with the same or higher performance. And that's clear to any of these technologies to be adopted, they have to not diminish the performance. And this means more efficient power converters. This is a more incremental process. More efficient refrigerators. That's limited by the Carnot process. And so there is some improvements that can be achieved there. Use of process heat. That's actually quite difficult, typically because process heat temperatures are not high enough to get much energy back. Energy efficient components. Superconducting technology is primary topic there, but also permanent magnets, high temperature superconductors, all have the promise to make more energy efficient components. And then energy efficient accelerator concepts, and this is mainly energy recovery accelerators, whether it's a electrostatic accelerator or an SRF linear accelerator. And finally, for the third factor, carbon neutral energy sources. As I said, besides hydropower and biomass, which is essentially just burning wood, which both cannot be expanded significantly, nuclear power is the only proven carbon neutral energy source that is scalable today, could be scaled today. The main obstacle to the treatment is the treatment of radioactive waste. Not really waste, but certainly not welcome. The accelerator-driven systems, accelerator-driven subcritical reactors, in fact, can transmute this waste and also generate more energy. So there is an opportunity for the accelerator community to contribute, as is happening, probably particularly in Belgium. The accelerator has to be highly reliable and very energy efficient, and we can do that. But now let me switch to some examples. And as I said, closest to my heart is the RIC Accelerator Complex. You see an aerial view here on the top picture. And in the bottom is the tunnel view of the two RIC superconducting rings. It's a very flexible and at present the only US Hadron Collider. It explores QCD phase diagram and the spin of the proton. The whole complex provides, the injector complex also provides beams for unique applications. We do medical isotope production, cosmic radiation simulations at the NASA facility, and we also have some commercial applications of our tandem right here. And we are very active in doing R&D for future facilities and accelerator applications, particularly SRF and beam cooling. So the performance of a collider can be improved dramatically by cooling the beams, getting a smaller beam spot, and therefore getting more luminosity. So this is a good example of how to get more performance without increasing the energy consumption. And so we developed a number of hadron cooling techniques at high energy at RIC. One of them is stochastic cooling using bunched beams and at 100 GeV per nucleon. So it's the first high energy bunch beam stochastic cooling. It operates at microwave frequencies at 10 gigahertz. And this shows how from initial luminosity evolution, which is shown in red, with cooling, much higher luminosity can be reached. And also something very interesting, namely the luminosity increases initially as the cooling gets more and more effective. The luminosity increases until you reach a peak, at which point particles are just lost from the collision. So you have burn off of the beam. There are no other losses of the beam at all. Very recently, we also developed the first bunch beam electron cooling for luminosity upgrade at low energy. It's not that terribly low energy, it's still in the GeV, but compared to the under GeV beams, it's low energy. Heavy ion collisions, that was also very successful and improved the luminosity substantially at these very low energies. And finally, we are exploring, have an experimental demonstration of a new type of beam cooling, coherent electron cooling, which is essentially stochastic cooling with a 30 terahertz bandwidth. You can see that's several orders of magnitude higher than for the microwave cooling, and therefore giving several orders of magnitude faster cooling, since cooling scales with the bandwidth. The information carrier for this stochastic cooling is, in fact, an electron beam, a high brightness electron beam. And this is the accelerator for this electron beam. As a result of all of this, our performance, the performance of Riko the last 20 years has steadily increased with record luminosities almost every year. Let me turn to ERLs. So ERLs were, in energy recovery linacs, were invented by Maury Tigner in a publication of 1965, and that's a graph from that publication, where there is a single RF cavity that both accelerates and then decelerates the same beam. So the energy is both given to the beam and then extracted from the beam. This is an arrangement which is not very typical for ERLs today. This is a more typical arrangement where the accelerated beam is turned around and brought back through the accelerating cavities in the same direction as the accelerating beam. And then after deceleration, it's dumped at low energy. So the key is that the beam that gets accelerated runs at the crust of the RF, whereas the decelerating bunches are at the bottom. There are many ERLs around the world now, some in operation, some under development, and some under construction. I just want to show one slide, and as I mentioned, you've heard about this extensively last colloquium, but C-beta Cornell Brookhaven electron test accelerator was specifically built to demonstrate energy efficient technologies. It's funded by New York State and is localized at Cornell. You see a picture of the hall with the linac on this side, and the return arc is on the left side. It's a multi-pass, so 4-pass test ERL with a single 4-pass recirculation arc. In order for that to work, that arc has to have an acceptance that can cover a momentum range of a factor of 4. This is way outside a typical beamline. So this beamline had to be built with extremely strong focusing, which required many quadrupole magnets, closely spaced, because closely spaced together, and also have a large aperture to cover all those 4 beams. And the only way to do that in an understandable way is to use permanent magnets. Because with permanent magnets, there is no distortion of the fringe field, or field that comes out, outside the magnet by the ion of the neighboring magnet. So you have undistorted field superposition, which can be very well understood and very well modeled. And the result of that was that the beam went through that line without almost any correction. After the beams would enter that channel, they would travel through it at all energies without much correction at all. And these are the trajectories. So this was very successful. You see here one of those magnets with the blocks of permanent material around here. This particular magnet is actually a combined function magnet. And so for the remainder, I want to talk about the new idea that we had, and that's using ERLs to build an electron-positron collider that uses a low amount of power. So there were many electron-positron colliders throughout history. The next electron-positron collider has to have high enough energy to reach new physics. So that's both precision measurements, but also search for deviations from the standard model. So it needs high luminosity and high energy. And beam polarization can be very helpful. There are really 2 energies that are of interest. So for single Higgs physics, we produce an H and a Z. And the center of mass energy needed is 240 GeV. And then for accessing the Higgs self-coupling, as well as the top Yukawa coupling, the energy has to be between 500 and 600 GeV. That's shown here in this area here, and the Higgs factor is down here. So there are, as you know, there are a number of electron-positron collider options being discussed, some of them for quite a while. There is the Future Circular Collider, EE, at CERN in a 100-kilometer underground ring. There is the CLIC collider using normal conducting cavities that are driven by a drive beam, reaching very high gradients. And there has been quite a bit of R&D done on this subject. And then, of course, it's the International Linear Collider, presently most likely to be situated in Japan, using superconducting cavities with pretty high gradients. That a lot of R&D effort has gone into that. And then there's the Chinese proposal, very similar to the FCC, with an electron-positron collider initially, also in a large 100-kilometer tunnel. So what is energy recovery LINAC collider? As I mentioned, it's a new collider concept using an existing accelerator, technologies, no new technologies required, and it combines the advantages of the existing collider concepts, namely from the storage ring collider. Storage ring collider recycles the beam many times, as well as particles. So does the ERL collider. And the linear collider is very efficient in using the collisions of to create events by having a very large disruption parameter. And that can also be done with an ERL collider. So both of these advantages are present in the ERL collider, and none of the disadvantages, we hope. So what's the concept? And that was, we published a paper last year. It's Vladimir, myself, and Maria. in physical speed. So how does that work? So we'd start with 2 damping rings, one for the positron, one for the electrons, where the beams are damped to very low emittance. They extracted 1 bunch at a time from each of these damping rings, and then put into again, 100-kilometer long tunnel, and accelerated in multiple passes in ERL with two superconducting linacs placed on either side of the collision area. Once they reach the top energy, they are collided, possibly in multiple interaction regions after collision. And the collisions have to be controlled to the point that the emittance doesn't grow too much, so that the bunches can be captured, recaptured, and decelerated in the same ERL, giving back the energy into the SRF cavities. During that process, of course, the RF phase is being adjusted so that now the beams are decelerating. After decelerations, the bunches are re-injected into the damping rings, and then the emittance is damped down again to the required low value. Typically thinking about a 4 millisecond damping time. That's 2 damping times in these damping rings. Any losses can be made up with injecting additional electrons or positrons. Also, we don't expect there to be many losses, beam losses. So why is the power consumption of such a collider low? So in an ERL collider, beam bunches collide only once, just like in a linear collider. So this allows a much larger disruption of the bunches by the beam-beam interaction, and therefore much more luminosity for a given bunch intensity. This is just simply a more efficient use of the beam particles. So this allows to either lower the beam current and therefore lower the synchrotron radiation power for the same luminosity, or allows to increase the luminosity for the same current, or some of both. In fact, what we look at is some of both. It's true that the linear collider can make the same efficient use of the beam particles, but the beam energy is not recovered. In fact, the beam is dumped after use and all the beam energy is lost, and that's actually quite substantial. In an ERL, all the beam energy is recovered during deceleration except for the radiated synchrotron light. A high energy ERL collider therefore can be much more energy efficient than a linear collider, as long as you have a large enough circumference. So the large circumference is required, otherwise the synchrotron radiation power is excessive. So what we looked at is for an FCC tunnel, 100 kilometer, 100 kilometer, and that gives a maximum energy of about 250 to 300 GeV beam energy, which you may recall is just the interesting energy for the double Higgs production. So this is a plot of the luminosity for various electron-positron colliders. The green line is the luminosity at various energies for a ERL collider that has 30 megawatts of total synchrotron radiation power. Just to be clear, that includes, in fact, the synchrotron radiation emitted in the damping rings. So that's the green line here, dark green line. And that's to be compared with the FCC-EE line, which is shown here in red. In fact, that's superior at the lowest energies, but then quickly the synchrotron radiation limits the amount of luminosity you can get. And this is for the ILC, or it's click baseline. ILC is shown here. Right. So for most energies, such a ERL collider can give you significantly more luminosity in some areas, much more luminosity in fact, in this intrusion area here, much more luminosity than either of the other concepts. As I mentioned, luminosity can be shared, has to be split by multiple detectors IRs. And there may even be possibility to increase total luminosity further by more beta star squeeze. So that requires more simulations. A key factor of all of this, of course, is that need to operate with a large disruption parameter. And that's a very delicate process. Like for the linear collider, the ERL collider would use flat beams. In fact, extremely flat beams. And that will minimize the beam straddling. Beam straddling is synchrotron radiation emitted by one beam in the field of the other beam. And in the magnetic field, generally, of the other beam. And a flat beam has a much lower magnetic field than a round beam. And so that minimizes overall the electromagnetic fields and minimizes beam straddling. It also turns out that flat beams allow for using 2D calculations to estimate beam effects, and that's what's done below. But of course, 3D calculations are needed eventually. So what's shown here is the vertical phase space, and vertical dimension is a small dimension, so that's the relevant dimension here. The vertical phase space of beam after collision. So the top is the middle of the bunch. That's shown here, and you can see for various distances in the horizontal plane. Remember, this is a flat beam, so it's a very wide beam. For various distances, the amount of phase space distortion you get is very different, but it's limited in either case. In all cases, it's limited to a rather small value. Not as small as it was initially, but quite small. Below here, this is the same thing, but for various various slices of the bunch, other than the middle, and still the whole phase space growth is limited. So the vertical emittance growth grows by about a factor of 5 in this situation, and is a very high disruption parameter. And that's well within the acceptance of the decelerating beam line. And in the other dimension, there is very little disruption or emittance growth. But of course, it needs to do 3D simulations that requires quite intensive computations. And one more thing, ERL collider recycles, as I mentioned before, electrons and positrons, and that opens the possibility for polarization as well. So after acceleration, collision, and deceleration, all electrons and positrons are re-injected into the cooling rings or damping rings, and only losses are made up by top-off injection. Depolarization during acceleration, collision, and deceleration are expected to be minimal. So during the initial simulations that we did showed that they are in fact very small. In fact, the flat beams help with depolarization during collision as well. So if this depolarization is less than the polarization buildup in the damping ring during the 4 millisecond time in the cooling rings, the electron-positron beam will eventually be polarized. You may have to wait a little while, but it will build up over time, and you can get pretty high polarization. We estimate between 50 and 70% beam polarization in both beams, electrons and positrons. Of course, this is just a concept at this point, and there are many, many challenges and R&D required. First of all, of course, it's a multipass, in this case, high energy ERL, and it requires R&D, transport, beamline lattice to preserve the small vertical emittance over these 100-kilometer distance multiple times has to be studied. And with this large aspect ratio, very flat beam. Full 3D simulations, as I mentioned already, after collisions with flat beams and high disruption parameters. Using small gap magnets to reduce power consumption. That's a real opportunity here. And consumption and cost of these multiple 100-kilometer beam lines. Also, it's interesting to do absolute beam energy measurement systems with accuracy of 10 to minus 5 at the IR. That's important for the physics. And that has already been pioneered at CBEF. High repetition rate extraction and injection kickers of the damping rings have to be developed, as well as compressing and decompressing the electron-positron bunches to match the energy acceptance of the 2 GeV damping rings. So we come to the summary. Energy efficiency is a worldwide issue. As a fundamental science community, our projects will need to include and address the needs of society to cope with global warming. Increased energy efficiency is one way to do that. And I just want to mention that projects that use hundreds of megawatts of electric power will be very hard to justify in the future. The superconducting RIC, the first heavy ion collider, and the first polarized proton collider is an example where energy efficient technology made higher performance possible. It reached record luminosity over a wide range with advanced beam cooling techniques. C-beta was built as a test energy efficient technologies. It is an ideal testbed for the development of compact high intensity ERLs. And compact high intensity ERLs could have many applications, such as intense X-ray and gamma sources, high intensity gamma facilities for nuclear structure studies, rare isotope production, and finally are essential for driving strong hadron beam cooling. The beams, electron beams needed for strong hadron beam cooling can only be accelerated by ERLs. Compact high-intensity ERLs also have commercial applications, such as for lithography and medical isotope production. The ERL-based high-energy electron-positron collider promises significantly higher luminosity at center of mass energies above 160 GeV, while consuming only 30% of electric power required for corresponding storage ring E plus C minus collider designs. Center of mass energy reach can be extended to 600 GeV for double Higgs and Higgs TT bar production. An ERL collider might be capable of colliding polarized electron and positron beams, which can open a new set of observables for the relevant physics. And these features of the ERL-based colliders are unique in this energy range. It outperforms the ring-ring design by colliding beams only once, and linear colliders by using energy recovery and recycling of particles. The ERL collider concept is, in fact, standalone. It does not need to be built on an existing injector complex. However, it would fit very well into the planned 100-kilometer FCC tunnel at CERN, but it could be built anywhere. And of course, as I mentioned, extensive detailed studies are needed to fully validate this concept. Thank you for your attention.